All right, we're going to get started. So today's class will be very interesting for both of us, you as the students and us as the teachers. First, we're going to go over the homework. We need someone to actually tell us what the homework was so we can go over it. If we don't have that material, we're going to go into buggers. Then Aaron, you.
So I've got a 0-day vulnerability that came in through the ZDI that I'm going to walk you guys through. It's actually going to be patched tomorrow, so it's 0-day as of tonight. I'm going to show you guys what a researcher gave us, which was crap, and then how we would go about reversing it, figuring out what the protocol is, and actually identifying what the vulnerability is. Unfortunately, that process is a little labor intensive, so it's probably going to run a little bit beyond the 8:15 mark this class ends. So if you're interested, stick around. If you're not, I'm not going to be offended. Feel free to leave. But it will affect your grade. Yes.
And we're going to take a break at 7:15, like a 5-minute break to give everyone breathing. So we'll be kind of that going forward. And yeah, it should be interesting because that will be used for IDA, that will be Windowbug, and we'll be doing it together. So it'll be interesting for everyone, including yourselves, to see how this goes. But so let's just take a look at the homework real quick. I'm going to try to do it from memory. Yeah, I think it's
So you guys have some form of a problem with that. Apparently the free version of IDA doesn't populate the names window properly or something, so you couldn't actually search for string copy.
I think it's Flirt.
Flirt? Oh, Flirt didn't pick it up. Flirt, if you guys don't know, is their IDA's like signature library thing, which automatically picks up like compiler-generated stuff and identifies what the library calls may be. I guess the free version doesn't actually pick up string copy, so you guys have a little bit of a
all right, so so the first thing was to go to string copy. So you view subviews names, then you're gonna hit Alt-T, and I'm gonna type in string copy, and it's gonna bring me to the string copy function. I'm hitting enter. And now I'm at the string copy call here. If I select the function and then right click, I want to get up. I hit X, I'm going to bring up the cross references. Now I've got string copy here. I want to chart the xrefs2 right here. And we can see this is the path to this call. This was the first homework, part of your homework was to take a screenshot of this subview. Does anyone have questions about that task specifically? No? Okay. The next one was to change the prototype.
The next one was to look up the buffer size.
Buffer size. So, thank you. So we click on the variable, the stack variable. We see that it starts at 10, x10 right here, and goes to essentially 0. So it's a 16. We hit OK, and it shrinks it, and we can see now the size is 16. That's the second part. Any questions about that part? No? No, we did prototype. So we next asked you to change the prototype of the function to reflect the fact that the variable here is not an integer. If we look at the prototype, we see that it's classified as an int. I'm first just going to grab the xref to this call, and we can see that it's just arg0, doesn't have any type information. If I go back, and I make it a car star, it now changed the type here, and if we go back, it propagated the information back up IDA. So IDA's propagated that prototype and the parameter name back up the call chain. Any questions about that? That was the homework. I think everyone probably got it. And yeah.
There's one more question you have to identify programming.
Oh, identify the caller.
No, the programming is not in the string call. The function that calls string call. program block.
Or like, what's
Yeah,
that?
I hear what you said.
Now, the
Like the
question
upgrade.
was, you have to identify the programming flaw.
Okay, so yeah, that would be the upgrade, right?
and copy.
So that would be who calls this, which is the same as doing something like this, or just looking at cross-references, see who calls it instead. Yeah, so traversing the call graph. But this is pretty straightforward. This was just so you guys get familiar with the actual UI and actually like
No, you have to identify a flaw in the function that calls string call.
the flow.
Flaw.
Oh, flaw, sorry. Okay, well, I mean, fact is, it's a static string copy.
You sure that wasn't last year's homework?
That was in the mail that that's
Either way, string copy doesn't take a length, so
Yeah.
it's an unbounded string copy to a static stacker
Oh.
variable. So if you control the buffer, then game over. Okay, let's get to that presentation. All right, so as you guys know, this is second portion of the reversing class. All right, so day one, or last week, we essentially covered static reverse engineering. There's two kinds of basic reverse engineering, static and dynamic. Static being where you're simply looking at a disassembly, you're not actually running the program, you're not attached with a debugger or anything like that. So I'm just going to quickly go over the differences between static and dynamic and why you may want to choose one or the other or combine the two. Why is that? What is it? All right, so there's a few shortcomings to static analysis. Essentially, what I have here is what you see is what you get. When you're looking statically, you don't see any of the dynamic information that may be determined at runtime. This usually is going to apply to C++ code, where you have multiple inheritance, and you have overloaded functions, and you have all these weird objects and stuff. The actual runtime state of the program, it changes. It has to know, it has to look up function calls and memory variables and virtual functions and all that kind of stuff dynamically. So you're not actually going to see it in the disassembly. So, for example, here you can see this is a call. As we showed you guys last week, most of the calls you guys are seeing were call function, right? In this case, you're seeing call, dword pointer, edx plus a. You don't know what edx is. In fact, it's probably dynamically figured out during runtime. So you're not actually going to see it, even just staring at this disassembly, unless you, there's certain ways you can do it if you're scraping what's called RTTI, which is runtime type identification stuff, but that's really complicated. We're not going to get into that. But I put here, nobody likes a busted graph. And what I'm trying to say by that is, if you're looking statically at something, and you look at that up graph and down graph, you can see everyone that this function calls and everyone that calls this function. If you're dealing with stuff like this, where it's dynamically figured out, your graph is going to be missing that cross-reference, so you can't actually see what's going on. So there's one example here, another example here. Another reason you want to do dynamic analysis is for resolving stuff like this. So as you can see here, we're in the data section. The data section is where I told you guys last week was where strings are located often and global variables. As you can see here, there are question marks. And what that just means is this is uninitialized. So when you're looking at it statically on disk, it's not actually running. These are not filled with any value at all. When you run the actual program, these are going to be filled with, maybe this is a global debug flag or some file handle or something like that. And there'll be actual values in here at that address during runtime. So this is just some stuff you're missing out. Another advantage to reversing dynamically is you get to see memory state, you get to see allocated buffers, you get to see how everything's actually operating. You get to see all the modules that are loaded. Granted, you can look at, there's things like dependency viewer, which allows you to look at an exe, see all the different loaded modules that it expects to load, and then all inheritance and all the different DLLs that all those modules load, and in turn you can see the entire state of it on disk, but it's not quite the same. If you run it in a debugger, you can just say, give me all the modules that are listed, that are loaded right now. And you get to see when they're loaded, why they're loaded. And you get to see things like open file handles. So statically, you may not see that this particular exe is loading a log file in the program file structure. But if you're looking at it dynamically, you can actually see that open handle. And we'll get to that a little bit later and show you some of the tools. And the most important reason that you want to be able to reverse dynamically is positive reinforcement. You're reversing statically, and there are a lot of people who prefer just to reverse statically, but I really feel like you're missing out if you do that. When you reverse statically, you see something and you guess as a reverser, you're like, okay, I think I know what this does. Oftentimes you're right, oftentimes you're not right. But if you are in a debugger and you're actually looking at that code, you're seeing what it's doing, you're stepping through it and seeing all the different values, it'll either reinforce what you thought it was, or it'll prove you wrong and make you reconsider it. So I call this section reconnaissance and empirical debugging. Essentially what this is you guys remember the attack surface stuff we mentioned? This is along those lines of things you want to do without actually using a debugger. So, for example, network I/O. Network I/O, as I told you guys before, is open ports, TCP, UDP, network ports. And we mentioned last week that you can use a tool called TCP view. There's some other tools we'll get into later, but essentially what this will show you is the IP address that a particular process name, as you can see here, is bound to. 0000 being the reachable remotely address, and then the colon being port. So for example, if you want to audit, this is actually from Nova GroupWise, GWMTA, MTA being mail transfer agent, you would know that, okay, it's listening to port 7180. If you want to be an audit, you're going to throw data at port 7180.
And the bottom IPs down there where they actually have IPs and local address we can't actually connect to.
Yeah, you actually
That's the
see,
example of not bound to open.
right. And then you've got, so that's TCP. There's also UDP, which apparently is not letting us show us, but we'll get to it later. But yeah, you can also use it with NetStat, which is built into Windows. TCP view, you got to run yourself. NetStat, ANO will give you that information. But anyway, yeah, here's the UDP stuff. So I just sorted it by TCP, UDP, UDP being here, same deal, 500, you can hit that with UDP. Pretty straightforward. What I mentioned earlier, open handles. This is really useful because say you're auditing a process and it has a log file. And then every time you fail an authentication or you fail a compare check and you're sending data at it, maybe it's logging. Maybe the developer's like, okay, we failed this, write it to the log file. So you can use tools like Process Explorer, which is also from Sysinternals. I believe Microsoft may have like bundled all these into their boxes. Yeah, well, okay, they bought Mark Zunovich. Yeah, essentially the guy who wrote all these tools. But you can just Google Sysinternals and find all these. Process Explorer is really, really useful for a lot of different things. So quickly, I'm going to show you this find dialog, find handler DLL. This is useful for a couple reasons, but here we're going to show open files, name pipes in this case. So if you do that find handles or DLLs, it'll pop up with a search where you can search for handle or DLL substring. In this case, I'm searching for the words named pipe, and that's just to find all the name pipes that are open on the system, regardless of the process. So you can see here, what's named pipe, and here's the actual named pipe, which you can pretty much reach remotely on most of these, although depending on the Windows version, they change that some of them require authentication, some of them don't. But this is something that people often overlook when they're auditing an application. They totally forget about RPC. But named pipe is really useful. There's, I mean, most of the work like Sasser and Ninda, CodeRedL, are using bugs that you could have found with this. And then you can also search instead of for just named pipe, you can search for open handles. If you view show lower pane in Process Explorer, you can either select in this sub-dialog, lower pane view. There are two options when you go in here. It's handles or DLL. So you can see all the loaded modules that it has, or you can see all the open handles that Process currently has. So here I have the all the handles, and you can sort them by type. So you can see all the desktop handles it has. You zoom out just a little bit. You can see all the files. You can see all the registry keys. And this is completely without a debugger. So you can just pick any process in your system and go, what files is it currently interacting with? In this case, we can see, so you have Windows System 32 something .log. So that tells you, okay, there's a log file. That might be interesting to look at while you're trying to audit this particular application. Along the same lines, you have error logging, which shows up in the event viewer. So on a Windows system, if you go start run and type event VWR, it'll pop this up right here. So the event viewer is a system-wide utility that it lets you log at different levels, application security system and IE. You can actually add more things to this, and there's an API for it. A lot of applications will often write warnings, errors, or just information, so different levels of information in here. And this is kind of useful sometimes as the developer uses it to pull debug information you might not otherwise have seen. In this one, you can see the master browser receiver server announcement from the computer, so and so. Not really that interesting, but there are definitely some applications that write stuff in here you definitely want to know about. This is a nice gem. ActiveX, like I said, has had thousands of vulnerabilities in it. I mean, this stuff is like the lowest of the low-hanging fruit. There are many tools to look at ActiveX. What you guys need to know essentially is, you're familiar with ActiveX, right? It runs in the browser. It allows, it's IE specific only. The different controls that ActiveX uses, in other words, the different modules that you're able to load in IE are represented by GUIDs on Windows, which is a unique, I don't know how many character identifier. They're all stored in the registry, and you can actually crawl the registry and find out which ones are what's called safer scripting. So just so you guys know, there's 3 different things you need to know about ActiveX to know whether you want to target it. Is it safe for scripting? Is it safe for initialization? Or does it implement iObject safely? If it does any of those, that means you can invoke it via a browser remotely. Meaning I can point any of you guys to a website, if that control is on your box, it'll automatically invoke without any prompts, which is really fun. The way you can see that, there are multiple tools out there. I mean, iDefense put out ComRaider, and then there's Axeman from HP Moore, and that's like that. And then you've got this one, which is my favorite, which is OLEview, and it allows you to you can actually sort. In this case, you can sort by controls that are safely scriptable. You can see all these right here. I selected one down at the bottom, if you scroll down here. In this case, so all these right here are default windows. And after reversing enough ActiveX, you get a pretty good feel for what's at default windows and what might be, a third-party application. In this case, that's definitely not, Windows. That's GW month control. That's group-wise month control. That's distributed with group-wise. In fact, I found some patches in there, so if any of you guys want some bugs, look at that. Because I didn't really take the time to vet them out. But so any of these controls have methods associated with them, and you can actually pull out those methods via OLE objects, and you can invoke them, and you can call those methods, and you can audit them. It's just another attack surface. If you guys are interested in that, you can email me, and I'll show you all the steps needed to actually audit them. RPC and namepipe. So I showed you how to find a namepipe via Process Explorer, right? So here's how you actually find it via IDA. All right, I wrote this little Python script, really useful. Okay, so firstly, you guys need to know that anything that's going to implement RPC, anything that's going to use a namepipe on Windows has to use the namepipe API calls that Windows exposes. Those are all defined in a specific DLL called rpcrt4.dll. So in your System32 directory, you guys probably all have it if you run Windows. All of these different function names that you see here are all defined in rpcrt4. The nice thing about that is you can say, look through all the executables on my system, find out which of those import rpcrt4, which of those require or make calls to any of these functions. And if they make calls to those functions, you can assume, maybe they have some form of RPC in there. So what I wrote, and I can just send this to the list if you guys want, it's called rpc search.py. You get a path, and it just crawls through, and it says, I found this function call and this DLL. And that's really useful. So once you locate a DLL that uses a namepipe or some RPC call, you can load it into IDA. So in this case, I loaded DHCP core6.dll, which is responsible for IPv6 DHCP stuff on Windows. And there's a plugin. There are a few ways to pull out the information. This is kind of hard to explain without some background knowledge. But in order to talk to an RPC service, you need to understand the protocol that it wants to speak. In other words, you need to know what's called its, I believe it's the IDL, Interface Descriptor Language, I think, which essentially says, okay, this specific RPC interface exposes X number of functions. For each one of those functions, it takes these particular arguments. So someone from Tenable, I think it was Nicholas Besley, is his name, wrote what's called MIDA. It's just a plugin to IDA. It's free. You throw it in your plugins directory, you run it, and it produces output like this. So remember the subviews that you have? This opens a new subview. It shows you the UUID, which is that GUID string. It shows you all the different functions that are available. It shows you where they're defined and an opcode. You can right-click any of these and hit decompile. What that's going to do is it's actually traversing all the IDL information that's in the binary to produce this kind of output. It shows you, here's the structure that one of these uses. And any of these, I don't have them on the screen here, you can actually see the function names. You'll see like function opcode number 0. It uses a struct, struct1, which takes a hyper, which I don't know what that is. I think it's a 64-bit integer. But then you've got, this takes a long. The cool thing about RPC is this stuff is so confusing that most people just don't even bother to audit it or don't even know it exists, and there's some really cool bugs there. I found a couple Microsoft ones that allow you remote code execution on Windows 2000 back in the day, which are really fun. And it's definitely tricky stuff to learn, which is why there's a lot of presentations of RPC stuff. But actually, former coworker of mine, Cody Pearson, and I wrote PyNSRPC. Google that. We made this all really easy for you guys. You can actually take a binary, it will automatically rip all this IDL information out for you, give you a fully working Python client that will talk to any of these RPC servers, which is pretty cool. And I can drop that link on the list if you guys are interested in that. Okay, so that's just a basic overview of the tools. You guys can just refer back to that if you guys are curious about how to do any of that stuff. I didn't really want to go into too much detail because we have a lot of material to cover today. So we're going to get to actually intro to debugging. There are a crap ton of debuggers out there. Debuggers for pretty much any language you can deal with. Debuggers back from 16-bit real mode days all the way up to 64-bit kernel debuggers, debug serve, all sorts of scriptable debuggers, interactive debuggers. IDA has its own built-in debugger. I'm just going to run through a couple examples so you get an idea of what the different types are, and then we're going to show you guys the basics of the WinDebug, which is what we're going to focus on because it's the most powerful and it's the one that Peter and I use. So just an example of some old school stuff. This is Turbo Debugger. This nobody really uses this anymore, but it's kind of fun for nostalgic reasons.
Yeah, nostalgic.
And then you've got stuff like, this is on all your boxes right now, debug.exe or debug.com. Not really used that much anymore, as you can see why. But you got some of the more complicated ones. This is the one that I think Peter and I both cut our teeth on. It's called OllyDebug. There's a variation of this called Immunity Debugger, released by Immunity Inc. The reason people like this one is it's got a crap ton of plugin support. It's really GUI centric. I mean, you've got your register view, you've got stack view, you've got memory views, you've got all sorts of, you can configure how out of this, change the colors, do whatever you want. It's really good for learning, but there are more powerful debuggers, and that's why we're going to teach you guys WinDebug before. But if you want an alternative, always not that. Here's WinDebug. This is actually Peter's theme. When you normally boot up WinDebug, it is really plain. It's just white with black text. But as you can see, Peter's has this assembly view. It has a where you actually enter your commands down here. You've got your registers here. You've got just a memory view, and you can change how all these are configured by all this. But we'll get into that when we go into the WinDebug primer. And you've got GDB. Have you guys used GDB before? All right. So you guys all know how much it sucks, right? GDB has horrible thread support. It's all based on ptrace. Yeah, I'm not even going to go into it. We're focusing on Windows, but GDB is out there. And this is PyDebug, which was written by my former coworker Pedram. And essentially, this is what we're going to refer to as a scriptable debugger. In other words, you write all the code for all the events you want to handle, and you just let it go. It'll catch events, and it's event-driven. It's not interactive. Like, you don't sit there and step. Instead, you just write what you want to handle and let it go. So like I said, there are essentially two kinds of debuggers. You have scriptable and interactive. Here's just some examples for your reference. These would be the scriptable ones, BDB, which is from the Kenshoto guys, where I believe the guys who run the DEF CON CTF. We've got PyDebug, I just mentioned. Ragweed is a Ruby version of a scriptable debugger. For an interactive one, you have Olly, WinDebug, Turbo Debugger, debug.exe. IDA's debugger is kind of both. You can interactively use it, or you can actually script it.
Now, a lot of people will have issues using IDA debugger. It's got a lot better reviews. You don't find people who are using IDA debugger versus Olly or WinDebug. That's what they do.
And the biggest reason, I think, well, in my experience, the biggest reason for not using IDA debugger is the fact that when you're using IDA, if you guys have noticed, you load a single module into it, an EXE, DLL, whatever it may be. When you use WinDebug or any other debugger, you attach to a process and all your modules are there. Whereas when you're using IDA, when a new module is loaded, it has to fetch it, disassemble it, put it in the whole thing, and it's kind of complex and it doesn't really work as well as some of the other debuggers do. But like I said, we're going to be focusing on WinDebug, and we're going to just jump right into the WinDebug primer.
All right, so like Aaron said, WinDebug is our go-to debugger, but we don't, we're not knocking except for GDB. The other debuggers, Olly, is completely acceptable, and it's pretty easy to learn with. There's a lot of right-click options, so if you don't know what's going on. There's a lot of ability to learn, which is why we both started on it. So WinDebug is pretty complex. There's, it takes basically command line options. You have to sort of know or have a basis of debugging to sort of know what you want to do or how to get started. Throughout this WinDebug primer, we're going to reference a command that is really important. I'm going to write it on the board, actually, because it's so important. It's .hh. It's really simple. And what that command does is invokes the WinDebug help. So if you have a question, .h, and then something here. And it will open up the WinDebug help. And the WinDebug help is really well documented. So it's a great place to start. And usually you can find what you're looking for. Like if you have a question about breakpoints, .hh breakpoint. It's going to bring up WinDebug, and it's going to have a section on breakpoints. So when you have a question, that's the command to go to. And if you can't remember that command, you can also just go like options or Windows help and then bring that up too. And we put two links up here. Maureen wrote this one. It's a bunch of WinDebug command references. And I don't know who wrote this one, but it's really in-depth Windowbug command references, and those links are available in the presentation to grab. So much like IDA, Windowbug allows you to configure your environment. And it's really important to do what works for you. I have different views for different things I'm doing. If I'm kernel debugging, I'm not as interested in the registers or having that be open than if I'm userland debugging or if I'm trying to run an exploit. So it really depends what you're doing. This is the vanilla, I just run Windows and I'm not attached or open to anything. You'll notice there's not much going on here. There's nothing going on here actually. And so you have only one view. When I open the one I've configured, I've got a bunch of stuff going on. I've got my disassembly here, so when I'm executing instructions, I can see what's above and below the instruction. I've got my registry window here. I've got memory at EIP and memory on the stack. Much like IDA as well, you have a Views menu button. You can click that and you can look at any of these. So you can see disassembly or call stack or memory. You can just open these up and then you can throw them. It's like IDA where you can drag things. I don't think you can drag things in the free version, but in a non-free version you can. This view, like in IDA, is also exportable via registry key. My coworker created this view, Stephen Davis, and we've uploaded the registry key that you can import to get this view. Again, disclaimer, it may not work on everybody. Look at it. It's you can open the file and see what's best. So in Windowbug, we've already said there's two types of modes, basically. You can attach to an existing running process, or you can open a new process. And there's benefits and disadvantages to both. When we attach, we're going to miss the initial execution event, which is usually okay. Like, we're going to miss DLL loads. So if we have a vulnerable DLL, we're going to miss the loading of that, so we can't set any breakpoints on that DLL right away. But we're also very quick to get to our receive loop or get to the point where we can feed it data. We don't have to wait for all these events to roll through. So those are two benefits. Another advantage or disadvantage is if we're attaching to an existing process, which means we're going to be less likely to want to restart that process, especially if it's like a service. Then we have to go in and restart the service. It's a little more time consuming than just opening the executable, running it, closing it, opening the executable, running it, closing it. That would indicate that it's less of a system issue. So this is what it looks like when you just attach. You can see here, Windowbug has listed all my loaded DLLs down here. I'm in the DLL debug breakpoint, which was fired off when the debugger attached. You can see I'm actually on a 64-bit machine, which is not a good example for this class, but here are my registers up here. I've got my memory at EIP, and my stack is right here. And this is what an attach looks like, because everything's already happened, so all the DLLs are loaded and everything's already there for us. When we open, we get a couple advantages. We stop the program before execution, which is a big thing if we want to know, for example, we know that there's a vulnerable DLL, and we want to know where it loads, so we can set breakpoints. We can actually set an event to notify us when our DLL loads if we go about it by opening the executable. So we essentially are there before the program even starts. The program's going to use the debug heap. Aaron's going to talk about that a little later, but basically it's a different heap, so you'll either see more bugs or less bugs depending on how the bug is supposed to be triggered. The fact that you're opening the process means you have more flexibility when restarting because it's not something that's already running. And this is what it looks like when we open a process. You're going to still have the DLL loads, but it's not. When you tell the debugger to go, you'll see a lot more DLLs loaded because it's just the basic DLLs that are imported. There's a bunch more that get imported when it runs. We break in another place. You can again see our registers, and this time you see our segment registers, then our x86 registers, our EIP, and then our stack. There's not much from the view that looks different when you do between the two, but it's really what your goal is. In our example this evening, we'll be attaching because the process is already run. We're interested in the DLL. It's part of an overall process. So we're going to be attaching to the process. And if you have any questions while we're talking, please again raise your hand. So Windowbug may be a little easier. Do you think it's easier than that? Probably. Yeah. So there's not as sharp a learning curve when it comes to navigating the UI, but there's some things to know about the UI. We've beaten to death the windows that you see here. The two things we want to draw your attention to are, this is where our commands go. When you see this .hh, you got to enter it into the command prompt down here, and then hit enter. It's also where all of our BP commands, any command with command line option goes in this text box right here. And this little indented thing is the status. And right now it's waiting for us to enter something. But you'll see it in this mode where, you can't see that, but it says busy. And that means it's not, you can enter a command, but it's not going to execute it because Windows in a wait for an event type of loop, and it's waiting for something to happen. Now, Aaron likes to hit control break as fast as possible and eventually he's able to get out of that loop, or you can just show that you have 5 seconds of patience and wait for it to come back to you. It's totally up to you. It's, I'm not judging, I'm just saying. So this just means it's waiting to do something, you're not going to get anything done, but you can try to break into it and stop that.
In other words, when the process is running, is the easiest way to say it. Or if you executed a command that Windows is thinking about, like if you try to tell it to break one on some symbol name that's not an address, and it's like trying to look up what the hell could that symbol be. It literally crawls through all the wooded DLLs and goes, okay, is this symbol that they asked for in this module? No. Is it in this one? No. And as it's doing that, it just says busy.
Yeah.
Wait while I try to do what you just told me.
And he doesn't, so he's control break, and you're good to go.
Well, if you see busy, you probably messed something up.
Yeah.
You could have been more specific.
Yeah. And just a great segue, perfect segue. Setting up symbols. Symbols are great. Microsoft releases symbols with their code. A lot of products don't. We're lucky they do. It basically gives you names for functions and global variables of their release code. It's not for every module that they release, but it's for a lot. They maintain their own release server, and it's this URL right here. What do you say?
First of all, I would say that it's more than just function names. It can be member variables, it can be inheritance information, it can be structures. It's pretty much all the type information that you lose. So right, you see source code, you see what the variables are named, you see what the functions are called, you see all that information. Generally, if you don't include symbols and you look at that in assembly, you see sub_address. You see just the actual assembly. You don't see any names at all. But if you have what's called a PDB, which is the symbol file for that module, then you actually in a debugger you'll see this called ntdll, and the function it called was called rtlallocate, right? And you actually see that, and you can pull all those are stored here. So when you set up WinDebug to pull down symbols for things that it can pull down symbols for, it'll greatly help your debugging.
And you can set up symbols either via just going File and Symbol Path or Control S, and we'll bring up this prompt right here, and you can paste this line in, and it's going to say basically download symbols contained here to this directory that are needed.
And we never remember that line.
Yeah.
Don't memorize it. If you go to windowbug.org, it has it right there, so you can just, every time I forget it, windowbug.org, control, copy, paste, go.
Yeah.
You'll see it just pull down all the symbols for all the different modules that you're currently loading in your process.
You can also set up the command line option and then do a .reload. Again, this would be in your command prompt window. It's really up to you which way. But symbols are really awesome. You need them, especially you'll see today we're going to use symbols to breakpoint and things like that.
And that's not just for Microsoft either.
Yeah.
Mozilla has a symbol store. Apple did until they took it down for whatever reason. But yeah, there's a bunch. 82, 5,000.
So we haven't gotten to breakpointing yet, but we're going to talk about events or exceptions. WinDebug is, as we said, interactive, so it triggers on events or exceptions, and that's when you interact with it. And you can configure what events and exceptions you interact with and on. So if you're seeing, we'll talk about the C++ exception, you can tell WinDebug to trigger on that and break, because currently when you'll see WinDebug, it'll just break and say C++ exception handled, and you'll just see it print. You won't actually see the debugger break on it. And that's a good indication that an exception is occurring in a try and catch block that you may be causing, but the program put it around it. So you want to see what's going on, see if you can maybe hit the exception handler or things like that. A couple other things, you can do this in command line. There's, again, if you want to know how to turn on all different kinds of stuff, see this right here. But a couple of ones we use, set exception on loaded module when this module loads. So basically it's saying when some module, and that's a wildcard, loads, break. So that's when you can say, okay, my DLL is home.dll. When it loads, I want to know about it, and then when it loads, you take that virtual address and you set up your breakpoints and you continue on. You can set things like, you can set an event for whenever a thread's created, whenever an access violation is created. And you can do this through the UI as well. If you go to debug event filter. And you can see here, there's a lot of, it goes, you can see the scroll bars in the middle. It goes up and down with all the different types of exceptions and events that you can trigger on. Initial breakpoint is enabled and handled. Here's the module load, it's ignored. That command above would actually turn that on. It's really up to you. This is the C++ exception. This is the one that's disabled. But when you're looking for vulns, this one you're going to want to turn that on.
Yeah, so you can set them in a bunch of different states. You can set them in notify, you can set them in enable, disable, you can make them do all sorts of things. The ones you guys should probably be concerned with are, like you said, module load and C++ exceptions.
Yes, the other ones are either set up correctly or
There's secondary stuff that you can't probably will never use. So.
WinDebug is a just-in-time debugger, which means instead of that Dr. Watson thing coming up and saying send my information to Microsoft, you can just get WinDebug to pop up and you can actually see what happened. And you can do that by just doing WinDebug dash.
And as a security person, I do this on my box just in general. All it does is it adds a registry key. And what that says is if any of the processes on my system crash with an unhandled exception, instead of letting it crash, I catch a debugger. So if someone's trying to copy you and their shellcode isn't working quite right, it's probably a good idea to have just-in-time debugger set up because you'll know. This actually happened to me once when somebody tried to pop my box and the shellcode didn't work properly. My just-in-time debugger popped up and caught it and I was like, well, that's interesting. Let's look at the call stack. Let's see what they were trying to do. And it's definitely useful.
So that's how you do it. It's pretty simple. All right, so now we're going to talk about the actual commands we can execute in WinDebug. We can disassemble code. U is essentially unassembled. So just U and then an address will print out a disassembly of however many bytes. I don't know the default byte.
20, I think.
20. If you specify B, it'll disassemble backwards. So you can see where you came from. That's really helpful, going backwards. And this is sort of, you can also do it on a symbol. So WS2_32 is the WinSock2 DLL. And it has a function called receive, which is what receives from the socket. Well, if I do U, WS2_32 bang, in the function name, Windows or WinDebug is going to resolve this to the actual address of receive. It's a lot easier than actually finding that address and throwing it into WinDebug. And then when you do that, you get the disassembly. So we have an example.
Well, one thing to note, right, so IDA is a disassembler. WinDebug has a disassembling component, right? So it's U because they call it unassembled, but it's essentially disassembling. But what you'll notice here is, this looks awfully a lot like IDA, right? Disassembly. The thing that's lacking, if you go back to it, is any analysis of any kind. See this right here? EBP minus 14x. Okay, that's a stack variable. If that were in IDA, you would see bar underscore something, because IDA's done some analysis and has done some cross-references. WinDebug doesn't do that for you. Like for the most part, you can't see what a lot of this stuff is. You don't have a lot of symbol names in some cases, and it doesn't resolve any stack variables, it doesn't do cross-references, it doesn't do things like that. So it's think of it as a rudimentary IDA. So if you, in fact, if you have IDA open and you have WinDebug open, you can just match up the disassembly and say, screw looking at the disassembly in WinDebug, let's look at it in IDA and get some symbol information, get the flirt stuff, which I guess you don't have in the free version of IDA, but there's a bunch of more information in IDA.
And ignore the black spots. That's to cut out some symbol names we didn't want to expose. So displaying data is really important. We're going to talk in a second about breakpointing and then displaying data is going to be even more important. But we need to display data. And one of the things we're going to display is registers. Because obviously, if we're trying to find vulns, we may get our registers into a leaky state. Or we may need to see what's in a register to determine, is it our buffer, is it our user data, is it the size? There's so many different things. So if you just type R, it'll do a complete register dump. So you can see all the values here. And then if you use R and then the @ and the register name, it'll print out what's in that specific register. And the reason that we use this @ symbol, you can just say R ESI and it'll so they show the same thing. But if you do @ WinDebug engine will just know that it's a register versus searching all the symbols. It's a little faster.
Also, just keep in mind, you guys don't care and shouldn't care about this entire line here, or pretty much any of this. You only pretty much want the register to care about EAX through EBP in this case. Most of the rest of that, it kind of was maybe daunting at first, when I first looked at this kind of stuff, but generally you can ignore most of that.
Yeah, it really, those stuff have no bearing on what you're doing for the most part. And a quick note, well, there's really not a lot of reasons, especially when you're doing bone stuff, why you do this. You can write to the registers, so I can move what's in ESI into EAX, or I can just do an immediate value. That's cheating if you crash the program though, so you don't really have a desire to do it. But you can do it. Sometimes I'll do it so the program won't crash because I messed something up, and then I can go back and do it again. And then it's still a little sketchy, but
But also to clarify, just because we haven't really broken down what all this stuff is, but just so you know, this part right here is the current instruction you're on, right? NTDLL and then an exclamation point. This is telling you are in the NTDLL module, you are at this symbol plus that offset, okay? So that's saying from the beginning of this symbol plus hex 2C is where you are right now. And as you can see, the EIP register right here is this value right here. That's the current instruction you're seeing. And what this is right here is the actual opcode bytes, like if you were looking at hex, beam, and IDA. And in this case, it's CC, which is an interrupt. But that stuff's good to know. In fact, while we're on the topic of symbols and all that, if IDA or if Windows doesn't actually have symbols for that particular module, like say it's a DLL. A DLL exports 4 symbols usually, like DLL entry point, DLL main, and there's a couple others. And what you'll see is if there are no symbols except for those 4 in a DLL, and you break somewhere in the middle of the DLL, and Windows doesn't know any nearby symbol, like it doesn't know the symbol of the function you're in, it'll say something like, DLL name, bang, DLL main plus a really large value. If you see anything that's like a plus a really large value, that's probably not the real function that you're in. You're probably somewhere in the middle of the binary, and it's going, this is the nearest symbol I know of. So you are, 3,000 bytes away from that symbol. It's just something to note when you're debugging. Yeah, better.
And then to display data, WinDbg gives a lot of options. There's a couple we didn't even include here, but you can display data as a keyword, a D-word, a word. Display data as bytes. You can display, if you have an address and you think it's an ASCII string, you can get WinDbg to print that out. Unicode string. You can display data as a D-word, and then it'll take each address and try to resolve the address to a symbol. That's helpful sometimes to see where you are or what's on the stack. I use that a lot. Same with the keyword. You can specify the L as the length modifier, so you can say DD, some address, then an L, and like 4, and it'll give you 4 of the keywords.
Also, just, you guys understand the difference between a value and a pointer, right? If you're going to do DD EAX, EAX is going to be, in that case, you can look at what is at EAX, but if you want to dereference a pointer, say if you want to dereference 4 pointers, EAX points to something, which points to something, you can use the POI operator. POI is for pointer at EAX. In fact, you can nest those. So you could do, if you happen to know what the structure is, you can do something like this. And it'll say, dump D-words, dereference EAX, and whatever you get, dereference that again. So it's kind of useful if you're like, if you know what the structure is and you're trying to follow some linked list or something like that, memory usually useful.
Yeah.
You'll see that a little bit later when we get to breakpoint. Because if you want to breakpoint on something and actually start dereferencing things, you can do that.
So this is what doing a DD at a register. This is in a debug session. This is actually a max length value, and then we have a bunch of ASCII strings and some A's. That's going as a D word. You want to go back?
I was just going to say, just to clarify how this is laid out, here are your addresses. EDI is this address right here. By default, it dumps however long this is right here. And this is the actual content. So, and it's split by 8 bytes, each one. Or 4 bytes, rather, 4 bytes. 32 bits. So EDI is actually this value. When you do EDI at EDI, you'll get all this. And if you were to do that POI operator, say at EDI, it would try to dereference this as a pointer and fail. But if there were a pointer there, it would dereference that and print out it's there.
Here's us using the length modifier, so it's just 8. And then here's DA, so you'll notice we're not doing at EDI anymore. We've added some I think it's 12 to get just to the string, and this is what the string is, so it looks like a web request.
A lot of A's and DA for ASCII, so say dump this as ASCII bytes.
And then finally DB, which is also pretty nice. It dumps it as a byte, so you just see each byte separated out, and then on over here you get the actual, whatever might be the ASCII representation. So it's broken down like if we've used a hex editor before, we'll explore similar to a hex editor. These are just a couple examples. There's a lot of different variations on the dump. There's a DC and a couple others we didn't cover, but those like the go-to ones we use a lot.
But .hh.
.hh, yeah, just .hh, DB, and you'll see everything. It's amazing. Okay, so viewing the stack, we're interested in this because if we set a breakpoint somewhere, we want to know how we got there. We want to know who called us, we want to know the arguments, and it'll allow us to speed up in the vuln finding process because the next time we set a breakpoint, we can be smarter about where we are. So if we set the first breakpoint on receive, we can determine who called receive, set a breakpoint after that, and we now have our buffer. So we're not wasting one step, and then we can get smarter and go further back down the call chain to where we really want to be with the vulnerable code. So
I was going to say, this usually works. Just playing a call stack in Windowbug, I'd say 80% of the time it'll work. Occasionally you'll do a call stack and it'll show one single item. And that's just because the way that it actually works, the way that Windowbug calculates these things, is it's actually stepping through ESP. ESP points to the stack, right? So it's stepping through all the D words at ESP and going, is that a code pointer, is that a code pointer, is that a code pointer? Remember the return addresses when I was showing you guys the stack last week? That's what it's doing. It's going, okay, that's a return address, add that to the call stack. That's a return address, add that to the call stack. Sometimes that'll fail. So sometimes you actually have to manually reconstruct the call stack by looking at ESP yourself. And that's kind of a pain. Yeah.
So what you can see here is the K command right here. When you do that, we have a couple things. We have the symbols of their resolved. So this was a breakpoint on WS2 underscore 32A. I'll zoom in real quick. And then we have the caller. So or we have the return address. So this is where this function is going to return to. And then we can see that WSOC32 is actually what called WSA receive, and WSOC32 receive is going to return to this address, which is right here, and it's some module that we blacked out a little bit, sorry. And then this is the address that it's going to return to. So we can actually back our way into what called the receive. In this case, this is the 80% case. And we'll be using that today or a little later on a lot.
Think of it as an updraft, right? It's the same thing, like when you're in IDA and you do an updraft and you see that all the possible ways to get somewhere, this is one path. This is showing you exactly how you got from A to B to C to D and so forth.
So this view has,
It's a little more complicated, actually. Yeah, I'll real quick. So what this view is trying to do is, you understand how the call stack is organized, right? You push arguments to the caller, or callee rather. You push the arguments and you push the return address. So what KV is trying to do is it's actually saying, can you zoom out just a little bit? Like here's your EVP, here's your return address, and here are the rest of the actual D words that were pushed to that function. So say with receive, you can look at this and go, okay, I know that receive is going to return here. That's the socket file descriptor. That's the destination buffer for receive, and that's the length to receive, 1 byte. So you can see the arguments to that actual function. Yeah, well, WSA receive and receive have different, I guess, function prototypes, but yeah, handle, and then size right here.
so you can see that 80%, it gets a little hinky, but in this case, because the buffer is, in this case, when we're reversing it, it's 5x500 is the receive length, and that's what actually would end up getting propagated to WSA receive. So in debugging, the biggest thing we do is stepping, or basically single stepping, and it allows us to execute one or a couple instructions and then pause and inspect the state of what we're doing. And that's a big part of debugging is, stepping over or stepping on, stepping through one instruction or a set of instructions. And we're going to talk about the two different kinds of stepping. You have stepping over and stepping into. What stepping over does is it basically says, I have a current instruction. The debugger sets a breakpoint after the current instruction and just executes until it hits that breakpoint. It doesn't, you don't see that part, but that's what it's doing internally. And we use that to, let's say we're debugging and there's a call to open process, right? It's a Windows API call that'll open a handle to a given process. There's a lot of code that goes on in open process. We don't want to step through every single instruction that Windows is executing because it's Windows code. We don't think there's a vulnerability there. We want to get past it. So instead of bothering going into and then waiting to go through all those functions and instructions, we step over the call and we just get the return value of that call to open process. Stepping into is the opposite. We would, if we hit T in Windows, we actually go into the function and we now step through all the instructions in open process. So it's useful when we either know the outcome of a function or we know we don't care about a function, we can step over it. But if we need to inspect what's going on within a function, obviously we need to step into that function. And there are different kinds of steps, and this is where you can speed up your debugging. You can step to an address. So if you know that you hit a breakpoint and you want to run 80 instructions to the next basic block you're interested in, you can just say PA and then that address, and it'll run to that address if possible. Then you can get really cute and say step until you get a call, or step to the next return, or you can say step to the next return or call. And basically all these commands in Windowbug say run until we hit a call or a return. And it's a quick way of either getting out of a function or getting to the next call you might be interested in. And we'll be using these today. And you can also step to the next branching instruction, which is, if you recall from the last class, some comparison or logical operation that created a branch, either jump if true or not true, and you can run and it'll stop there and you can evaluate that comparison or that branch and know where you're going. So it's a quick way to get to the state that we're interested in. And it's that sort of separates people who know what they're doing in Windowbug versus not, because they can quickly get to where they need to go, and we'll be using those commands today.
Yeah, it'll make a lot more sense when we're actually running through an actual live debugging session. You see a basic block that's this large in IDA that you don't want to sit here and step through every instruction. You just go, I want to know, does it go left or right? PH. It just jumps you right there. You go, okay, it goes left. You continue.
So this is going to be a pretty contrived and poor example of stepping over. So let's just, we're doing, whoops. What just happened? Okay. Cool. We won't do that again. So we dumped our registers, and as Aaron already talked about, we see the current instruction is a call, right? And we've already reversed this function, and we know we're not interested in it. So we look at the instruction sequence after it. So we see a call, and then a move EAX. Let me try zooming again, not failing. There we go. We see a call, move EBP and EAX. Okay, we want to get to that instruction. We don't want to go in and step through this function call. So we use the command P. It steps over the call, and you'll notice the next instruction we hit is move EAX. And we can see here's the value of EAX from that function call. So we just got the result of that function call very quickly instead of having to step through it. And you can see when we disassemble again, we're now at that move. Our EIP is now where we want it to be after that call. So it's just an example of us using it. It's very helpful, especially if you're not interested in going into a lot of the API calls or functions you already reversed. All right, so we've made reference to it, and here it is, breakpoints. Breakpoints basically a way, who's heard of breakpoints? Who knows what they are already? I mean, you have breakpoints in every compiler has its own debugger, it's pretty standard stuff. It's basically a way we can pause a program or specifically a thread. The debugger can inspect what's going on. Being smart with breakpoints, and we're going to show you some examples, some pretty cool breakpoint stuff, is fundamental to being good at finding holes and quick at finding holes. Because you may want to set a breakpoint that gets hit 1,000 times, but there may be only one case you're interested out of that 1,000. You need to know how to exclude the rest. So we're going to talk about that. So we have two types of breakpoints. We have hardware and software. So hardware breakpoints, you have a limit of 4 because hardware breakpoints utilize DR registers, and there's only 4 DR stands for debug registers. There's only 4 debug registers in your processor, so there can only be 4 hardware breakpoints. Hardware breakpoints allow you to put, what you do is you put a virtual address, or an address, of course. You put an address into the DR register, and whenever that address is accessed for read, write, execute, it'll break into the debugger with an interrupt of 1. These are great for breaking on access, so Aaron's going to show you a little later on. When we set a breakpoint on a receive buffer, we're going to see every time that buffer is touched by other instructions because we're breaking on access through the DR register.
Probably the quickest way you can reverse something is with a hardware breakpoint. I'll show you exactly how to do that.
Software breakpoints are what are most commonly known. Software breakpoints are interrupt free, and the opcode is CC. We saw a couple images ago. And you supposedly have an unlimited set of software breakpoints. I've had experiences where Windowbug chokes out at about 800 breakpoints, but Aaron says he doesn't have that problem. If you compare our computers, you can see why he doesn't and I do. So hypothetically, you have an unlimited number of software breakpoints you can set. They're used, basically what the debugger does is it overwrites whatever values at that address with CC. When that instruction's hit, it breaks in the debugger. The debugger then restores the byte. So you as the user never see the CC there, even if you go to disassemble or unassemble that block where you put the breakpoint, it hides it from you. So where do we set breakpoints? Well, obviously this is going to sort of coincide with a lot of stuff we talked about last class where we said, attack surface or code coverage. We want to set breakpoints at entry points, data entry points. So receive, we talked about it, we've seen examples. We're going to use that today. That's where our data is getting into the program. That's where we want to breakpoint so we can see where our buffer's going and who called us. We can use the backtrace with those breakpoints to see how we got here. Read file is another example of user data getting read into a program, and you want to know where that call's going as well. You can also use it for comfort, to know what's in a value. So we saw this slide, or we saw this image already, but you want to know what EEX is. You want to know specifically where in the program this call is going. And then you can add a comment with that address and then click around to it, which is very helpful. So confirmation. And you also want, having a bad day, I apologize. Yeah, it is. So you also want to go set breakpoints as we talked about on user-controlled data. So you can very quickly determine what's touching or what's accessing our data, and that's going to be where you want to start reversing. There's no reason to reverse the whole program when most of the program's not going to do anything that has to do with our data. But when we pinpoint where our data is being touched, we can very quickly start reversing that, and that's very helpful.
That'll totally make sense. So like, imagine combining a code breakpoint. So you breakpoint on receive, and that's where your data is actually coming in on the network. Your data is now in the process. You set a memory breakpoint on the first byte of it. You let the process go. As soon as that program decides to read from your data and start doing something with it, the debugger breaks. Really easy.
So why are we going to do this? Pretty basic reason. Dynamic resolution, where we have that call some register plus something or some register. We want to know where that's going so we can see where in the program we are. We can use it to pinpoint parsing routines, such as setting the breakpoint on that buffer, seeing where we're being touched. Great. We also want to identify access to global variables, things like that, and we can use the debugger and breakpoints to see when our global variables set or who's accessing things like that. And finally, we want to determine control flow. Sometimes you look at a disassembly and you see branches and stuff like that, and you have no clue why it's branching or where user data influences a branch, and you really have to use a debugger to determine that. And that's a great example of why we need to use debuggers. Because there's no point in wasting tons of hours trying to figure that out when you can just open up a debugger, set a breakpoint, and then run. So how do we do this? Great question. Setting breakpoints. We can set breakpoints on code. It's very simple. BP, breakpoint, our module base, exclamation point, the symbol name or function we want to breakpoint on. So in this case, we're breaking on a heap allocation function. We can also breakpoint on registers. So you'll see Aaron tonight. We'll get to a certain stage in the program. We'll want to just break. We know we've gotten to a point now where we can get to it again reliably, and we're interested on a branch or something like that. So we're going to change the payload that we send to influence it. So we're just going to set a breakpoint where we currently are, and that's basically what this does. Is it sets a breakpoint at the current instruction or act, which is nice. You can also breakpoint on a wildcard, which is awesome. Aaron showed me this recently. I hadn't seen this before, but it's really awesome. You can just say some module and then a search term. So you could do ntdll asterisk heap asterisk, and it would set a breakpoint on every symbol name that contained the word heap in it. That's a lot of API calls it's going to breakpoint on. So here's an example of what it looks like in WinDbg. We want to focus on here. Oh, these are all.
Run through them in order.
Yeah. Well, we're going to get to these in a second. We're going to focus on this one first. This is just setting a breakpoint on every API call that had read file in it. And you can see WinDbg's outputting set breakpoint on read file EX, set breakpoint on NT read file scatter, read file again, and then the import read file. So that's a lot of breakpoints it's set, and just it's sort of like a machine gun approach to breakpoint setting, and then essentially you go back and you figure out which ones are valid or not. But it's a great way to just set breakpoints on what you think will be there. You can also set breakpoints on data, and this is where the hardware registers come in. So you can breakpoint on read access at the address of ESI the ESI contains, we'll read the first byte, so reading one byte.
So you can do that with, so the way to read this, breakpoint on access, this can either be, I believe, R, W, or I think X2. So you can say read, write, or execute. So VA, R1 at ESI. That's saying R1, this could be 1, 2, or 4. 1 bytes, 2 bytes, or 4 bytes. So this is saying break on access if a single byte is touched from starting where ESI is. This would say if 4 bytes are where EDX are.
And read is actually includes write in this case. Write only includes write, but read includes read, write, according to .hh. So we can see here, this is very simply looking, that's the command in window. It enters the breakpoint in there. So we can display breakpoints. A lot of times we've set a bunch of breakpoints and maybe we have a thread running that's hitting one of the breakpoints we set a while ago. We want to see the list of breakpoints we've already set so we can disable it. BL does that. And you can see right here, the BL command is executed, and then it shows you, the address that the breakpoint was set on. In this case, we had read1, read4, and you can see the symbol name that it was set if there was one, and also any command that was attached to that breakpoint. So that's how that view breaks down. You also have the E means enabled. So you have enabled, and if they were disabled, you have a D. So you can disable the breakpoint as well. So to clear all breakpoints, you just do BC star, and it clears all the breakpoints from that list. If you want to disable a specific breakpoint, the breakpoints are numbered. I'll go back to that list and show you they're numbered. You can just do BE and then the breakpoint number you want to disable. And if you want to enable a breakpoint, it's just BE and that number again. So we can see here. First, you can see the breakpoint number right here. So 0, 1, 2, 3, 4. We can see we disable 2, we delete 3, and then we list them again. And you'll notice that 3 is 7C, 9, 1C4, and that's been deleted. It actually doesn't return to you that number. C3 is missing. And then BE asterisk enables it back all along. So you can use asterisk to do all of that. So you can get really cute with breakpoints. In this case, there's a breakpoint at EIP. We're going to display the contents of the address that's ESP plus 4 points to. So we're going to dereference ESP plus 4 and print that to the debugger, and then our G means continue. So we're just going to do that and then continue. And that's a good way to see what's going on for you, to see where you are and things like that.
So in that case, like if you're going to do, say, a string copy, say EIP was pointing to the beginning of string copy, you said breakpoint at string copy, dump at, dereference ESP plus 4, that would be argument 0, considering ESP 0 plus 0 is the return address, ESP plus 4 is the first argument, ESP plus 8 is the second argument. You're saying, dump me that pointer, actually dereference it, show me what's there, and then go. So what that'll do is, anytime string copies hit, it'll just be printing out and then continuing. Semicolon allows you to specify multiple commands at once. So you can just say, every time string copies hit, just print out that buffer so I can see what's happening. So that's really useful in a lot of different functions. You'll see later.
We have another one here that's an actual logical expression. It's this again is going to dereference argument 2, in this case ESP plus 8, and it's going to say, is it greater than the max word? And if it is, it's going to print out blue and then pause the debugger. And if it's not, it's just going to continue. And this is an example of being in some kind of loop or something where you're only interested in one specific aspect of the program and you only want to break if that's true. I've used it before when I'm looking at string parsing. I know what byte I want to break on, so I'll set something like if AL equals that byte in hex, break or echo something, and then if not, just continue. And it's a great way to just hit where you want to be.
These things can get really, really nasty. I mean, it's actually like almost a full programming language that you can put inside that conditional breakpoint. You can say like, take this variable's contents, dereference it 6 times, dereference that, add 12 to it, assign it to a temporary variable, and then later on reference that temporary variable again, see if it's less than this, and do whatever. You get, I've written some of these that were probably like 4 or 5 lines long for some complicated examples.
And here's, what it's just the command entered into window book. And again, you don't want to see the output, but it's just the command in window book. Okay, so perfect timing actually, quite literally. It's 7:15, so we'll do a 5-minute break. Everyone can rest up a little bit, and then we'll start back. Cool.
All right, so if you look at stack view in IDA, you know the size of all of these. You know that, say, here's a 40, this is 40 bytes, that's 20 bytes, 32, 256, 20, 48. You know the size of all of this. It's static, it's not going to change. Very simple stuff. That's stack. So the opposite of stack, which is obviously static, is going to be heap. So I'm kind of curious, how many of you guys know what a heap is? Okay, a couple people. So the heap is it's dynamic memory. It's memory that can be resized. It's memory that's not necessarily contiguous. Any API call you see that anything that's calling malloc or new or free or delete is generally using heap. Okay. I'm going to show you a little bit of an analogy in a second after I show you what this looks like in assembly. That'll probably make a little more sense. But anytime you're seeing a malloc call like this, size can change. That isn't necessarily 16 bytes all the time. So that buffer can be different. You can also realloc buffers, and then you can free buffers. So malloc and free, the opposite of each other. In the case of C++ code, you can see things like this. See that IDA commented this operator new. If you guys are familiar with C++, you know what that is. The reason it's messed up like this is due to what's called C++ name mangling. In IDA, you can go to options demangled names in IDA, and then you can click this. And then what that'll do is it'll change it so it actually makes sense in operator names, which is pretty useful. So anytime you see any of these API calls, it is it's going to be dealing with dynamic memory, which is the heap. So like I said, stack's straightforward. And the heap is simply a memory manager. There are a bunch of different implementations of this across Linux and Unix, different variants of Unix. There's PHK malloc, JD malloc, which is Jason Evans malloc. There's Microsoft low-frag heap, Microsoft debug heap. There's a bunch of different variants of dynamic memory manager. We're going to be focusing on Windows just because Windows has support for that, and that's actually what the walkthrough of the bug is that we're going to talk about. So here's the simplified version of the heap, right? You guys are familiar with Battleship? Anyone? Okay. Imagine this is the heap, right? If you make, all right, so if you make a call to malloc, right? It allocates something on the heap somewhere, and that's determined by the algorithms of the heap. So that's just this memory manager going, what's the most efficient place to put this allocation, and it places it there. You request something like malloc 30, it goes, okay, we're going to put it here. Next. And then it updates it. So essentially every heap chunk, and these are going to be referred to as chunks from here on in, they're linked by pointers, forward link and a backward link. So think of them as, you guys are familiar with linked lists. In this case, it's a doubly linked list. So heap allocation, heap allocation. So when you call malloc, you actually get you get a pointer to one of these heap chunks back. Okay? So you call malloc 20, you get this. You call malloc 30, you get this. So they won't necessarily be next to each other. In fact, often they're not, and so forth. So just scroll through these, right? Here's another allocation of some more, and then it updates like so. More allocations. So you can see how this is getting fairly complex now, right? So that's why the heap has what we call coalescing, which is essentially defragmenting. So when the heap decides that it's messed up enough that it's becoming inefficient to actually traverse those data structures, it'll reorganize things. So if you actually call free, say we're going to free this big guy, you'll see that all the pointers got updated. So now it's like this. And when it coalesces, it'll sometimes put these in a line, it'll sometimes do whatever it thinks is efficient, and that depends on the implementation. So we're just showing you this kind of stuff because it's a little bit more pertinent when you get to the exploitation. This heap exploitation is a pain. Okay, so that's the basics on heap. You have stack and you have heap. Simple, right? Stack and dynamic. All right, now this is probably the most interesting part. Vulnerability analysis, which is the name of your class, so this should be pretty pertinent to you guys. We're going to cover two general methods of analyzing vulnerability, right? You can work what I call forwards or backwards. Forward being, okay, I'm going to start at the point of input. So this is the network proceed, this is the read file, or what have you. And you're going to step from there and see, okay, how do they sit there and analyze my data? What are they doing? How are they modifying it? What are they looking for? And you're working, pretty much from bottom up. The other method is working backwards. This is, in my opinion, a lot harder, but this is something that we have to do quite often at ZDI because somebody will give you a file and it crashes, and you're like, great. Especially when it's a file format. Maybe they changed the byte that was 60,000 bytes into the file, right? You don't want to start at read file and sit there and reverse the entire file format. You have to work backwards. You have to start at the crash and go, okay, let me start looking at the call stack and see where we came from. And this can be a huge pain in the butt because you've got, you know, if it's a stack overflow, it's going to mangle the crap out of the stack, so you don't even know where you came from. You look at the call stack and it's a bunch of A's. You're like, okay, great. I don't even know where to start. Which is why there are a lot of different techniques we're going to show you to kind of help you. We have things like just-in-time debugging, which Peter mentioned. You have the crash dump. You can kind of look at the registers and understand what's going on. There's some ways you can cheat. My favorite way to cheat is G-flags, global flags. This is something that's distributed with debugging tools for Windows. Essentially what it is, it's a UI, or it's actually a command line version 2, that sets registry flags for particular processes. Okay, so this is what the UI looks like. If you install the debugging tools for Windows, which is how you install WinDebug, you'll have G-flags. When you open up G-flags, you have 3 tabs up here. The only one you guys should really be concerned about is this image file. Here you'll put your process name. So in this case, I put iExplore. Then you hit tab to refresh, and you have all these crazy options you can do. I'm just going to go through some of the more useful ones. Okay, so stop on exception. So Peter mentioned earlier how, say you're a C++ developer, and you're not too confident about the routine you're writing, and you want to make sure that if it crashes, the process doesn't entirely die. So you might wrap it and try accept finally, something like that. By default, the debugger will not catch that exception. It might notify you, hey, the C++ exception occurred, but it won't throw an access violation. So that's not good for someone who's trying to find bugs. You actually want to know exactly when in fact, you could actually be corrupting memory. You could be hitting an actual heap overflow, which is corrupting memory, and the process actually catches that and goes, we're going to continue anyway, which is kind of dumb. So stop on exception is really useful. And then you've got debugger, which is really straightforward. This is, just look back at the UI down here. You check debugger, and you put the full path to WinDebug or AllDebug, wherever you want here. And what that does is as soon as that process is started by your computer, it will actually attach a debugger. It's pretty useful for catching it out. I use that a lot with CGIs. Okay, so say you have a vulnerability in the CGI, Common Gateway Interface executable, right? It's a process that's not running. A web server is running. You hit that web server with a request, and it goes, oh, they're trying to get this CGI, let me launch it. So then it launches that CGI, and does whatever, and then crashes or whatever. If you actually want to catch it when it's started, you can set the debugger flag. So as soon as that web server goes, okay, they were looking for the CGI when it started, then your debugger catches it. You can debug it from that point forward. This one's really cool too, user mode stack trace database. So I showed you guys calls to malloc, right? When you make a call to malloc, by default, you don't know what that call stack is if you're not sitting there stepping through and seeing the actual malloc happen. Let's say you have a crash that occurs way later on, and it's say a heap overflow. So you're debugging something, it crashes in a memory copy that's overflowing a heap, and you know where that heap chunk is because you're seeing it get overwritten, but you don't know how big it is. You don't know who allocated it. You want to know what its size is, you want to know how it was allocated, do you influence how big that heap buffer is, and so forth. If you turn on user mode stack trace database, every time an allocation occurs, it actually stores on disk the entire call stack to that allocation, which is really, really useful when you're trying to debug something. And finally, my favorite, PageHeap. PageHeap's awesome. PageHeap is, for every allocation that occurs in the heap, put an entire, what's called a guard page behind it. And a guard page is simply just a huge chunk of memory that if it's ever accessed in any way, written to, read from, it alerts the debugger with a guard page violation. So I assume you guys can imagine when that's useful, right? You allocate a 1,000-byte heap buffer, and you have PageHeap on. Right behind it, it puts a guard page. Now, as soon as that's being copied to, as soon as that first byte copies beyond the end of that buffer, PageHeap kicks in. So if you're trying to actually debug a heap overflow, you want this. Unfortunately, there are some really weird side effects to it. Well, first of all, it's going to make everything really, really slow. If you're debugging dynamic memory and it's allocating 10 bytes, let's put your guard page behind it. Allocating 100 bytes, putting another guard page. I accidentally had this running on Outlook for like 6 months, and I had no idea why it was slow. I never played it on Outlook code. It turned out I had PageHeap on, and every allocation was pretty much double in size. Another weird scenario that you might run into, just as a caveat, PageHeap, due to the fact that it's actually allocating something and putting a guard page behind it, and then allocating a guard page and so forth, the actual distance between pointers can change. So a lot of code, C code, if you guys I assume you guys have written some C code at some point, maybe you've done pointer math, where you take this pointer and that pointer, and you subtract them, and you're like, okay, there's this much distance between them. If you have PageHeap enabled, you might have like this much distance between them. In fact, I had a bug that I was trying to reverse for, I kid you not, 5 years in Flash, Adobe Flash. And the reason it was such a pain to debug is because it was heap corruption, and because if I turned on PageHeap, it would not trigger anymore at all, because it was due to pointer math, which is a huge So G-Flex definitely helps you. We talked about the heap a little bit. Windowbug has another way you can cheat here called bang heap. It's just an extension of Windowbug. So I told you that heap is essentially a bunch of doubly linked lists. That's an oversimplification. The chunks are doubly linked lists, but they're part of some other structure, which is part of some other structure, which is part of something which eventually is linked to the PEB, the process environmental block. What bang heap does is it goes, okay, let's start at the PEB, let's go to the heap element, right? And it goes and it starts crawling every single linked list throughout the entire heap, all the free lists, all the look aside lists, like all these substructures, and it just ensures that all these doubly linked pointers are actually pointing where they should be. So this is really useful if you're reversing something and you're like, okay, I think this function call right here is going to corrupt the heap. Let's run bang heap before we do anything. Okay, everything's intact. Step over the call with P. Now do bang heap again, and it'll tell you something's corrupted. Really useful because you can kind of triage where the bug may be. And this is a neat trick. I call it seeing into the future, or virtual machine debugging. This is where you guys know what virtual machines are, right? Being a workstation or box or virtual PC or any of that. The steps are essentially, you say you got a process running, you're attached to it, okay? You have a specific state of that process right now. Go to VM, snapshot, take snapshot. When you take a snapshot of that, you're taking a snapshot in time of that process, everything exactly how it is so that you can actually revert back to it later. Okay? You name it appropriately, and then you cause the crash. So then you supply it with the data that you know is going to crash it, and you see what happens. When that crash occurs, you're going to see things like the actual heap address that was being corrupted, right? So combine that with bang heap. So say it was a heap overflow. You see that it just overflowed some heap buffer, you see the address that it was trying to write to, and an access violated. You're like, okay, so it's corrupting some buffer in memory. Well, I'd like to know where that buffer was allocated from. Use bang heap-p-a address will tell you, if you had used the stack trace database on which I mentioned earlier, here's where it was allocated. Now you have an address, you have a call stack, you know exactly who allocated it, hell, you even know its size. So now what you can do is write down a little notepad, okay, at this address, there's going to be a call to malloc, it's going to be of size 1024, we'll say. So you can set a breakpoint, revert the VM back to its original state, set a breakpoint at that malloc for a specific size, like a conditional breakpoint that we were talking about earlier, so saying, break here if the size is 1024. Then you run it again to try to crash it. When you do that, you'll actually be able to catch the very first, you'll catch it as soon as it's allocated. This is before the crash occurs. Now you're like, all right, sweet. I have a heap buffer, I know where it's allocated. Now you set a memory breakpoint on write on the very first byte of that. Then you let it go. As soon as it's written to, the very first time, the debugger will break. And you're like, okay, now I know exactly where the heap overflow starts. And then you don't have to worry about debugging it from a crash. You kind of like step back in time. Does that make sense? Yes? Okay, cool. All right, so here's the fun part. Okay, so we got this bug a few months ago via the ZEI. It's a bug in